Yes. So basically, we need to have an idea about the unit step function, then this impulse sync function. So why we need this unit step is actually so you can simply replace this kind of pulses or this kind of a staircase functions using unit step. So rectangular type pulses and staircase type of type functions or signals. So if you have rectangular pulses or staircase type of signals, you can simply use unit step function to replace these forms. So then you can do any kind of a mathematical manipulation for these unit steps, rather keeping it as a rectangular pulse or a kind of a staircase pulse. So I explained two examples in the previous video. So the second is unit impulse. So we can utilize unit step, unit impulse to simplify certain functions. So we discussed it previously, and the third important block is sync function. So sync x is actually defined as the magnitude of 1 at x equals 0 and sine x over x for x not equals 0. We know that if we say x equals 0, you cannot define sine x or x. So then using a kind of a different approach, they basically evaluate the sine x or x at x equals 0. So it's defined as 1. Then for x not equals to 0, you can simply evaluate the sin x as a ratio of sine x or x. So then we can clearly identify when and where this sync function gets 0 values, or so these are the 0 crossing points. So we know that once the sine x goes to 0, so you can have the 0 crossing point. So sine x is 0 when x is 5, 2, 5, 3, 5 and so on. So then you can easily identify the crossing points. So then if any function can be replaced using sync function, you can plot the behavior of this particular function using the sync function. For example, so let's have this kind of, so we have a function xt which is equals to half sync phi t. So this is the one example. So we know that, so sync phi t, so we can easily identify for which t values, for which t values, the sync phi t gets 0. So we know that, so the inner argument, so inner argument should be, so the inner argument should be a kind of the multiples of 5. 5, 2, 5, 3, 5, 4, 5 and so on. It means like we can simply uh, capture this whole component by using n phi. N is a kind of an integer having 1, 2, 3, 4 and so on. So similarly, we can identify that the inner argument here is 5t. So 5t should be n times 5. So the argument should be a kind of a multiples of 5. So from this we can simply say that t should be equals to n. N is actually c, sorry, c, let's say 1, 2, 3, 4 and so on. So then we know that the sync phi t is 0 at n equals 1, 2, 3 and so on. So if you draw this one, So if you draw this one, so it's something like that. So we have xt equals half sinc phi t. So we have t-axis. So this is 0. So this is n equals, so t equals 1, t equals 2, t equals 3, and so on. So this is something like that. So this is -1, -2, and so on. Here it's half. So this is actually half sinc phi t. So we know that when t goes to 1, 2, 3, and so on, the sinc phi t gets 0, and for t equals 0, this sinc phi t is 1, then the value at t equals 0 is half, not 1. So likewise, you can, like for example, you can have like a sinc 2, 5, or 3 into 2. So whatever. So then if it is this, you can simply argue that the inner argument should be a kind of a multiples of 5. So then 2 5 t over 3 should be n into 5, the multiples of 5. So from that you can simply get the equation for t should be like 3 and divide by 2. So we know that n is equals to 1, 2, 3, 4, and so on. This is plus or minus. So then you can simply say that t should be once n equals 1. So it's like this. N equals 2, 3, n equals 3, 9 over 2, n equals 4, 12 over 2, and 6, like that. So you can easily find the 0% point. So from this, you can easily find the 0% point. 0% points means these points. So likewise, if you have function in sinc format or as a sinc function, you can easily plot the function. So then other than that, yes, then exponential functions. So this is another important quantity, exponential functions. So exponential function, so you can mathematically define it x equals a kind of a magnitude e to the power 80. So this is the exponential function, exp function, exponential. So e to the power a kind of. So so a may be greater than 0 or a may be less than 0. It means like this whatever the exponent term, this is the exponent. So this is the exponent. This may be kind of a positive value like a e to the power 2t. So now here a becomes 2, which is greater than 0. So again you can have this negative exponent. So it's like this. A e to the power minus t. So in this case, a equals -1, which is less than 0. So depending on the values of a, so if a greater than 0, so you have this kind of a function. So this is a greater than 0, for a less than 0, you have this kind of function. Okay. So this is kind of a diverse type function. So this is a kind of a convergence. So the amplitude here, so the amplitude of this function is continuously increasing when a greater than 0. For this type of functions, where you have a negative exponent, so this function is simply converges to 0. So its the amplitude of the function is continuously decreasing and converges to 0 when this a goes to, so a is simply a kind of a negative value. Okay. So these are basically real exponential functions because a is a real quantity, a is a real quantity, a is a real value. So then you can have like whatever the real quantity is for a. So if this real quantity is greater than 0, so you can have kind of a continuously growing function or exponentially increasing function or diverse type of function. If the exponent is negative, so you can simply have a kind of a converse type of function where this amplitude of the function is simply decreasing. So these are the two types of real exponential function. So the real exponential function can be defined like that. A is the amplitude. For example, we know that e to the power 0 is 1. So then here the value is a. In this case, a. So once this a is positive value, you have this kind of a trend. A is negative, you have this kind of a trend. Okay. So what about this function? E to the power minus at ut. Um, yeah. So then, without this unit step, if you just focus on e to the power minus 80, so this is something like that. So this is e to the power minus 80. Because this a minus a is, for example, in this case, a is greater than 0. So minus a represent a kind of a negative value. So then we have this negative exponent and the value of this or the ultimate value of the function is like converged type of function. So this is actually e to the power minus 8 without this unit step function. Again, we know that the unit step is something like that. So this is a kind of a function. So this is ut actually. So once you multiply these two quantities, so we can clearly identify, so these individuals values are simply multiplied. So this value is multiplied with the corresponding value of the function, and this is multiplied with this one. So these values are simply multiplied together and get the output. So during this block, the unit step function is simply 0 because from its definition we know that the unit step function is 0 for t less than 0. So this is actually t less than or equal to 0. So then whatever the values come from this exponent is simply suppressed to 0. And whatever the values appear after t equals 0 is simply multiplied by 1. So then these magnitudes are simply multiplied with 1s and these magnitudes are simply multiplied with 0. So the result is actually this kind of a function. Px plus 1. So this is actually e to the power minus at ut. So what happens is if you multiply this function with unit step, so it basically truncate the function and extract the positive component only. So it means like, so once you multiply this one, simply extract this block. And simply remove. So then by using unit step functions, you can truncate the function. Truncate a function. So by introducing unit step, you can simply truncate a function. So, so now we basically cover this real exponential function. So we have kind of idea what happens to the or the to the behavior of the function when this exponent term a in this case is greater than 0 or less than 0. So then once you multiply it using unit step function, you can simply have this kind of a truncated version of this exponential function. Okay, what happens if a function is like this? So you have another function xt, so it's like e to the power minus a t minus 1. T minus 1. So this is actually, if you draw it, you can simply say that it's something like that. This is your xt. Because from this one, ut minus 1, so this is a kind of a shifted version in time domain by 1 unit. So this is ut minus 1. So the original ut which is actually starting from 0 is shifted by 1 unit. So this is ut minus 1. So then once you multiply this exponential term by ut minus 1, you have this kind of a shifted exponential. So this is kind of a e to the power minus a t minus 1 ut minus 1. So again a kind of a truncated version using a shifted version of unit step. This is a shifted version of ut. So the second thing, what happens when this A becomes a complex number? What happens this A becomes a complex number? So if A is a complex number, we can simply model this as a kind of this. So the sigma and omega are kind of real numbers and J represent the complex domain. So this is the real component. So this is the real component of A and this is the imaginary component of A. So omega is the imaginary component of this complex number A and sigma is the real component of this complex number. So we can in general write A or represent A as sigma plus j omega. So then if you apply it to here, so the original function xt is actually e to the power at. Now A is actually sigma plus j omega. So we can simply substitute A with this e to the power sigma plus j omega into t. So we can simply multiply this by t separate and separate this exponential. So we have this sum of this powers. So and we can simply write it as a product of these two exponents. So we have sigma t into the power j omega t. So we know that sigma and omega are real values. So sigma is a real value. So we know that. So then this is actually this block itself is a kind of a real exponential function. So this is a real exponential function. What about this? So this becomes a kind of a complex exponential function. Because here the exponent is a kind of a complex number, j times omega. It's something like 2j minus j 4j kind of. So it's a kind of a complex number. So the second part of this function is a complex exponential function and the first block is a kind of a real exponential function because the sigma is a real. So j times omega times t is a kind of an exponential quantity in time domain. So e to the power j omega t becomes a complex exponential function. So then what happens? So we can apply inverse transformation to expand this e to the power function. So we know that e to the power j theta. So e to the power j theta can be converted into cos theta plus j sin theta. So e to the power j theta, which is a kind of a complex exponential function, can be transformed into a kind of a rectangular type of format using cos theta plus j sin. So then we can apply it here. So then this becomes e to the power sigma t, e to the power sigma t here we have, instead of e to the power j omega t, we have cos omega t plus j sin omega t. So we have this e to the power sigma t here, and this complex exponential is converted or transformed into a kind of a complex number cos omega t plus j sin omega t. So from this, so we can have this the real component of xt. So the real component of xt is this e to the power sigma t times cos omega, e to the power sigma t times cos omega t is the real component of xt, and imaginary component of xt equals e to the power sigma t sin omega t. So then we can plot these real and imaginary components separately if you want. So this real part of xt equals e to the power sigma t cos omega t. So how do you plot it? So this cos omega t actually. So you know that cos omega t, something like that. So this is actually plus 1 and minus 1, this cos omega t, something like that. So this is actually, so let's assume like for the moment sigma is greater than 0. So then this is something like that. So then the product of these two becomes this. It's something like that. So this is e to the power sigma t cos omega t. So we have this exponential function where the sigma greater than 0, you have kind of a exponentially growing function, and cos omega t is a kind of a periodic function which fluctuates between plus 1 and minus 1. So once you multiply these two together, you have this kind of a function. This is a kind of a cosine type of function, but the magnitude of the cosine function is simply increasing. So the magnitude is increasing. If the sigma is less than 0, you have this kind of version. So it's kind of a function. So it basically, so this is the envelope of the function. So envelope is actually to the power sigma t. So the cosine function, the pattern of the cosine function is remains as it is, but the magnitude of the function, cosine function, is either continuously increasing or continuously decreasing based on this e to the power sigma. So this is the real component of this xt. Similarly, you can plot the imaginary component of xt. So it's very similar. So this is the imaginary component of this xt. So then the function is, these trends are very similar. So rather having this cosine, you have the sine function. So it's something like that then. So it should be sine function. Like that. So then in addition to that, so you should be aware of this transformation. So if you have a kind of sine omega t kind of, you can convert the sine omega t into a complex exponentials like this. So so this is the case, like sine omega t can be converted into this. So this is like valid for both. So if you can convert, so if you have a function like this, so you can convert back into cos omega t. So if you have this kind of, you can convert into sine omega t. Again, if you have sine omega t, if you want it to convert it to complex exponential, so this is the transform. So this is very useful because if you remember, so one of the examples in Fourier series, we asked like if your xt is sine omega t, so you are asked to evaluate the Fourier series. Fourier series. So the Fourier series, if you remember the basic definition, so this is the basic definition of the Fourier series. K equals minus infinity plus infinity sum ak e to the power jk omega t. So it means the very simple idea here is, so xt is simply represent using these kind of complex exponential functions. So kind of so x, if you can convert this xt into this kind of complex exponential function, so then it's a kind of a Fourier series of xt. So based on that assumption, we convert this into complex exponential by applying this transformation. So then we have e to the power j omega t minus e to the power minus j omega t divided by 2j. So then we rearrange these terms and come up with this kind of expression. 2j e to the power minus j omega t plus 1 over 2j e to the power j omega t. So then if you expand this one, we know that, so we have a0 at k equals 0, then k equals 1, we have a1 to the power j omega naught t, a2 we have this, and a minus 1 we have this. So likewise we have distance. So then by mapping these two together, we can simply identify. So this is actually refers a term for k equals 1, and this basically refers to the term k equals minus 1. So then, for this case, this is the Fourier series expansion. So this is the Fourier series expansion. A0 is 0, A1 is 1 over 2j, A minus 1 is minus 1 over 2j. So this basically has two terms, not the infinite number of terms, so it has two terms. One term is this, so the other term is this. So this is the one coefficient, so this is the other. So we need this conversion, we need this conversion when we need to apply for Fourier series search. So for example, if you have another example, let's assume this x equals 2 cos omega naught t plus 3 sin 2 omega naught t. So this is our function. So if you are asked to evaluate the Fourier series, so convert it to exponential by substituting this. Convert the sine to omega naught t by substituting this. So then we have 2 cos omega naught t. So you can simply say that j omega naught t plus e to the power minus j omega naught t divided by 2. Then 3 here, sine, you can replace this 2j omega naught t minus 2j omega naught t divided by 2. So then, so we have to rearrange these terms, which is it simply aligns this pattern. So we have to take constant to the middle of the expression, and this positive exponentials to the right hand side, and negative exponentials to the left hand side. So it means like you can bring this one to the right hand side. So here we don't find any kind of a constant. So for example, if it is like plus 1, so I have plus 1 here. So then this is the constant. So this will be the actually A0, and this contributes to k equals 1 case. So this contributes to k equals 2k. So you need to find the corresponding coefficients. So this contributes to k equals minus 1. This contributes to k equals minus 2. So then ultimately we have a kind of a series expansion having 5 terms. K equals 0, k equals 1, 2, minus 1, minus 2. So by rearranging these terms, you can easily find the coefficients of these individual frequencies. So this is also kind of a very useful conversion when we think of Fourier series. Okay. So the other thing, so there's another function which is in the slides. So it's a kind of a rectangle function. Rect function. So it's simply defined as RECT bracket. Here, in the numerator, we simply explain or write the domain, whether it's a kind of a function of t, or if it is a function of x, then you put x here. If it is a function of z, so you can put z here. If it is a function of omega, you can put it omega here. So here, so tau, this is the pulse width. So it's a pulse width. So if you draw it, it's something like that. Here the magnitude is 1. Here it's tau by 2. Here it's minus tau. So this is this. So keep in mind, so this rectangular pulse is always symmetric around 0. Symmetric around 0. So from the definition itself, this rectangular function is symmetric around the 0. And this basically represents the pulse width. So then this is your pulse width. So this is the pulse width. So then half should be happy in the positive side and the rest of the half should be happy in the negative side. So take this one. Correct. Example. Omega divided by 2 omega. Solid void. So your independent variable or the domain is actually omega. So a rectangular path. And here the magnitude is 1. So the pulse width is actually 2 omega naught. So then this is actually symmetric over the 0. So then this becomes omega naught. This becomes minus omega naught. So this becomes 2 omega naught. So this is a rectangular. Okay. Can you write rect t over tau using unit steps? Can you write? Or can you represent this rectangular pulse using unit step? Yes. So the rectangular function is something like that. So you can do like that. So we can generate one unit step like this. So what is this actually? Sorry, so we can write it here. So we can introduce one unit step. So what's the function of this one? So this is shifted to the left hand side. So then this becomes u t plus tau 2. So ut is something like that. So this is the ut. So this is ut. So this becomes a kind of a shifted version of ut to the left hand side of the time axis, so then it's become ut plus the shift t by 2. So then similarly you can add another function like this. So this is actually u t minus tau over 2. So ut is shifted to this right hand side of the time axis by t by 2. So then it's a kind of a ut minus t by 2. So what happens if you subtract ut minus tau by 2 from ut plus tau by 2, you have this rectangular path. So then ut plus tau by 2 minus ut minus tau by 2. So then rectangular parts can be represented using this. Okay. So what about this function? So can you write this? Write it as a rect function and combination of unit step. So we can easily write the xt as a unit step. So we can have one unit step like this. So this is actually t minus 1. So the other unit step is something like that. So this is actually t minus 3. So then this block actually can be represented as u t minus 1 minus u t minus 3. Okay. So how do you represent xt as a rectangular function? So the original rectangular function is something like that. So it's symmetric over the t-axis. So we can think of like this. If it is symmetric, so this is the symmetric axis, which is at t equals to. So then it means, so the pulse width is actually 2. So once you map it to this one, so this becomes tau equals to 2. So then tau by 2 becomes 1. So this is 1, this is minus 1, and this is 0. So this kind of a square rectangle pulse is shifted to 2. So the 0 point moves to 2. So then we can simply say that, so this original rect function is shifted by 2 units. So this block represents the shifting of original rect T over 2 by 2. And this represents the pulse width. So this any kind of rectangular pulse can be represented using unit steps, while you can stick into this rectangular pulse. Keep in mind, if it is a rectangular pulse, it's by definition itself, this rectangular pulse is a kind of a symmetric rectangle around the zero axis. So this numerator simply represents the domain of the function or the random variable of the function, and if it is shift or not can be accommodated in that variable, and the denominator you can simply highlight the path width of the function. Okay, so these two are actually so then we basically discuss couple of functions. One is unit step, so then unit impulse, and third one is actually exponential function, real or complex. So then a rectangular function. Other than that, this is by default, the sinusoids. So we know that in general, any kind of a sinusoid can be represented using that. So this is the peak amplitude. This is the phase shift. So these are the important functions and in this signals and system. So you basically go through this one. So I shared this slide set and a couple of videos which describe this stuff. So you go through these ones, and so we'll next time try the Fourier transform. So up to now, we basically study a Fourier series representation where you have given a kind of a periodic function and how do you map it to frequency domain. So the next would be Fourier transform rather than this periodic function. If you have a kind of a periodic signal. So if you have a periodic, a kind of an unperiodic signal, how do you map into frequency domain can be discussed through this Fourier transform. So we'll do it in the next Monday. So if you have any questions, you can ask it now, or you can drop a message to the chat box or discussion forum, or you can mail. So if you have any question, just ask it, or else we'll wind up the session. And if you have any queries about the session, you can drop kind of a message to the since text box and since discussion forum, or just drop an email. So any questions? Else if you don't have, so we wind up the session. So thank you for the participation.
Thank you,